Have you ever wondered how complex software systems are designed and structured to function seamlessly? Just like a well-designed building, a successful software system is the product of thoughtful and meticulous architectural design. This process shapes the skeleton of the system, its components and their intricate relationships. It's a blueprint, a guiding light that illuminates the path for developers as they breathe life into the software. And just like a universal language, once you grasp it, you can create, evolve, and understand any software. Understanding architectural design is like learning the language of software construction. Architectural design in software engineering is the blueprint for system construction. It's like the master plan of a building, outlining the system's structure, components, their relations, and interactions. But what does this design process involve? Let's decode it. Firstly, we have system decomposition. It's like breaking a complex puzzle into smaller pieces. System decomposition involves partitioning the system into manageable components or modules. This helps to identify the functional and non-functional requirements and allocate them to suitable architectural elements. Then comes the component identification. Think of these components as the building blocks of our system. They represent units of functionality or responsibility. In this stage, we identify and define these building blocks, considering factors such as cohesion, coupling, and reusability. Next, we look at how these components interact with each other. The architectural design specifies the communication protocols, interfaces, and data flows between components, ensuring seamless integration and interoperability. Now let's not forget the architectural styles and patterns. These are like the reusable templates that provide solutions to common architectural challenges. Examples include layered architecture, client-server architecture, microservices architecture, and event-driven architecture. Quality attributes are also a crucial part of architectural design. These are the non-functional requirements of the system, such as performance, reliability, scalability, and security. Architectural design incorporates mechanisms and strategies to optimize these attributes throughout the system's architecture. Then, we move on to deployment and distribution. Here, the design addresses how the system will be deployed and distributed across different environments and platforms. It considers factors such as scalability, availability, and fault tolerance to ensure robustness and resilience in deployment. Lastly, we have the design rationale and trade-offs. Architectural design isn't just about making decisions. It's also about documenting the why behind these decisions and the trade-offs made during the process. Each of these aspects plays a critical role in shaping the architecture of a software system. They come together to create a comprehensive blueprint that guides developers in implementing and evolving the software. Let's delve deeper into these aspects to understand how they contribute to effective architectural design. First up, system decomposition. Think of it as a complex puzzle. You wouldn't try to solve it all at once, right? Instead, you'd break it down into smaller, manageable pieces. That's exactly what we do in architectural design. We dissect the system into components or modules, each with specific functional and non-functional responsibilities. This way, we can focus on each piece separately, ensuring every element gets the attention it deserves. Next, let's talk about component identification. Imagine a bustling city. Every building, every street, every park plays a role. Similarly, in a software system, each component has its unique function. Identifying these components is a critical step in architectural design. It's about deciding what the building blocks of your system are going to be. You'd look at factors like cohesion, how closely the responsibilities of a component are related, coupling, how much one component depends on another, and reusability, the ability to use a component in multiple contexts. Now, these components don't exist in isolation. They need to communicate, interact, and work together to create a fully functioning system, much like how different departments in a company interact to achieve common goals. Defining these component interactions is a vital part of architectural design. It's about determining how data flows between components, what communication protocols to use, and how to ensure seamless integration. Onto architectural styles and patterns. These are tried and tested solutions to common architectural problems. Think of them as templates or blueprints that you can adapt to your needs. You've probably heard of some of them: layered architecture, client-server architecture, microservices architecture, event-driven architecture. Each has its strengths and weaknesses, and the choice depends on your specific requirements and constraints. Quality attributes are the non-functional requirements of the system. These are the characteristics that define how well the system works. Performance, reliability, scalability, security. These are all quality attributes. Architectural design is not just about what the system does, but also about how well it does it. It's about incorporating strategies and mechanisms to optimize these attributes, making sure the system not only meets its functional requirements, but also delivers a high-quality user experience. Deployment and distribution might sound like afterthoughts, but they're integral to architectural design. It's about planning how the system will be rolled out across different environments and platforms. Factors like scalability, availability, and fault tolerance come into play here. A well-designed architecture ensures that the system can handle growth, withstand failures, and deliver consistent performance across various deployment scenarios. Finally, we have the design rationale and trade-offs. Every decision in architectural design comes with its pros and cons. It's about balancing different considerations, constraints, and priorities. Documenting these decisions and their rationale provides valuable insights into the evolution of the architecture. It helps future developers understand why things are the way they are and guides them in evolving the architecture further. Understanding these aspects gives us a comprehensive view of what goes into designing a software system's architecture. But how do we ensure effective and efficient architectural design? Through principles, of course. At the heart of architectural design, we find two guiding principles: modularity and abstraction. These principles serve as the foundation, shaping the way we approach and implement software architecture. Modularity is all about decomposition. It's the principle that encourages us to break down the system into smaller, more manageable components or modules. This approach enhances maintainability, as changes in one module don't necessarily affect others. It also promotes reusability, as modules can be used across different parts of the system or even in different systems. And lastly, it aids scalability, since we can easily add, remove, or replace modules as the system evolves. On the other hand, abstraction is about simplification. It's the principle that guides us to hide unnecessary details, allowing us to focus on the essential concepts and relationships within the system. By doing this, we're able to understand and manage the system's architecture more effectively. Moreover, abstraction facilitates communication among stakeholders, as it provides a high-level view of the system, devoid of complex, low-level details. In essence, modularity and abstraction are like the yin and yang of architectural design. While modularity breaks down the complexity, abstraction hides it away, creating a harmonious balance that fosters efficiency, maintainability, and scalability. These principles serve as the pillars of architectural design, promoting efficiency, maintainability, and scalability. Architectural design is not just about creating a structure, it's about creating a robust, efficient, and scalable system. As we wrap up, let's revisit the core elements of architectural design. It all begins with system decomposition, breaking down complex systems into manageable components. These components, the building blocks of the system, are then identified and defined, bearing in mind aspects like cohesion, coupling, and reusability. How these components interact is also paramount, dictating seamless integration and interoperability. We use architectural styles and patterns to tackle common challenges and optimize quality attributes like performance, reliability, and scalability. The deployment and distribution of the system across various platforms is also a crucial aspect of architectural design. Lastly, we document the rationale behind design decisions and trade-offs, shedding light on the considerations and constraints that shape the architecture's evolution. So, the next time you marvel at a software system's functionality, remember the architectural design that made it possible.